Dr. Rico here. This is a lecture from my course, Math Foundations of Engineering Analysis. The syllabus link is in the description. Hello, and welcome to this lecture on nonlinear analysis. I'm giving it the little short word or acronym NLIN for nonlinear. And this is the first of a few lectures that I'll give on nonlinear systems, their general properties, characteristics, when they arise, and then also some simulation techniques. Just sort of an introduction to this area of nonlinear analysis, which is of course quite large of an area. So the ubiquity of nearly linear systems and the tools we have for analyses thereof, as we've seen many of in the past in our engineering education, can sometimes give the impression that nonlinear systems are somehow exotic or even downright flamboyant. However, a great many systems important for a mechanical engineer are frequently hopelessly nonlinear. Here are some examples of such systems. A robot arm, okay? The analysis of the dynamics and kinematics of that robot arm lead to a nonlinear dynamic model. Viscous fluid flow, usually modeled by the Navier-Stokes equations, which are nonlinear partial differential equations. Non-equilibrium thermodynamics. And non-equilibrium thermodynamics are thermodynamics that occur away from what's called thermodynamic equilibrium. And it's the type of analysis one wants to do when one is interested in the transport that's happening. So maybe diffusion, maybe separation that's occurring. So concentration of materials that can happen in fractional distillation, for instance, refining different petroleum products, concentrating different substances, chemical or otherwise. I did a dissertation on the concentration of spin in very tiny mechanical systems. So that's a whole other topic we won't get into. But needless to say, the thermodynamics there are nonlinear. Anything that fills up or saturates. An example would be the dynamics of a fluid system that has a barrel in it that fills up and overflows. It can no longer hold the capacity of say, water that it was holding before. So anything that fills up or saturates where it maxes out and it stops behaving in the same way. Nonlinear optics, okay? We're going to return to this one. Lasers are part of that. Einstein's field equations for gravitation in general relativity, very nonlinear, the curvature of space-time. Heat radiation and nonlinear heat conduction, both topics of interest to the mechanical engineer. Fracture mechanics. So it's a topic that's definitely a sort of graduate level topic, but the mechanics of when a material starts to develop cracks and breaks in the material itself, breaking those bonds, those atomic bonds that are required to break for a material to fracture in most cases. And we will also include here the three-body problem, or the n-body problem. But 3 in particular is famous. And this is the mechanics of having 3 bodies in mutual gravitation, with each other. This problem is very nonlinear. Gravity is a nonlinear phenomenon. When you get distance away from the massive body, and you can and you're dealing with similarly sized or similarly massed bodies, they interact with each other's gravitation in a nonlinear way. So the three-body problem is also nonlinear. So these are the types of things that you would encounter, three-body problem in orbital mechanics, for instance, or if you're doing aerospace engineering. So the trajectories of bodies in space. Okay. Lest we think this is merely an inconvenience, the nonlinearity of these systems, we should keep in mind that it is actually the nonlinearity that makes many phenomena useful. Okay? It's not just an inconvenience. For instance, the laser, I mentioned a little earlier, depends on the nonlinearity of its optics. It wasn't until we decided to start using that nonlinearity that we were able to identify the mechanism that drives the laser. So similarly, transistors and the digital circuits made thereby, including the famous microprocessor, wouldn't function if their physics were linear. So despite linear mechanics, linear physics being good models of many physical systems, and despite many of those physical systems being very useful, there are some systems that are nonlinear, and not just hopelessly so in the sense that we can't get rid of that nonlinearity and it's a pain for us, but we can actually use that nonlinearity in our designs, and that's a very powerful tool for a mechanical engineer. In this chapter, we will see some ways to formulate, characterize, and simulate nonlinear systems. Purely analytic techniques are few for nonlinear systems. Okay, purely analytic are few. Most of these analytic techniques are beyond the scope of this text or this lecture series, but we describe a few, mostly in the lecture to come in the Nonlinear chapter nlin.car, which is the characteristics of nonlinear systems lecture in a couple lectures from now. Simulation via numerical integration of nonlinear dynamical equations is the most accessible technique, so it is introduced. Okay, so we will be introducing that method, the numerical integration method for nonlinear dynamic systems, but we're not going to get into the details thereof. We're just going to learn at a very high level how to use some tools in Python, actually, to do some numerical integration of nonlinear equation. We skip a discussion of linearization, okay, which is the way that in the past, you've probably often encountered nonlinear systems and then immediately attempted to linearize them. And that's a great technique. And we should use it. We should prefer this if it's an option. But instead, we focus on non-linearizable So that's what we're going to be taking a closer look at in this chapter, sort of an introduction to these types of systems. There are many, many things that can be said beyond what we cover here, but this will be somewhat of an introduction for you. For a good and more in-depth introduction to nonlinear dynamics, see the Strogatz and Dichter text, and the reference is given at the right here. And a more engineering-oriented introduction is Kolk and Lehrman, which is given in reference 3 on the side over here. So you can check out these references if you want to take a deeper dive. But in this chapter, we'll take a look at some high-level properties of nonlinear systems and start to get to understand them a little bit. So Thanks for watching, and tune in next time for the next lecture in this chapter on nonlinear systems. See you later.